Welcome to CSE Colloquium. We have Matei Zaharia from UC Berkeley. I'll keep this very short. Matei is just an amazing distributed systems and cluster computing researcher. He has won the Best Paper Awards at SIGCOMM and NSTI last year, and today he's going to talk about big data and how to make big data analysis go pretty fast.
Thanks for having me here. So I'm going to talk about making big data analytics fast. And I want to encourage people to ask questions throughout the talk if they have them. That will definitely make it more interesting. So what is the big data problem? I think everyone's very familiar with this. I'm not going to go into it in too much detail. But essentially, the problem is that in a lot of domains today, data volumes are growing faster than the speed at which we can compute on them, especially with traditional systems. And it's due to three different trends. So first of all, the data sources themselves are accelerating. We have things like the web or the mobile web, where increasing numbers of users are using it and it's generating data very quickly. And we also have things like scientific instruments, gene sequencing machines, or telescopes that actually improve at a rate faster than Moore's law in their ability to generate data. So there's all this data coming in. At the same time, storage is quite inexpensive. Storage has kept up with Moore's law, and it's dropping in price very quickly in terms of capacity. So it's cheap to actually store all this data. But the ability to process it isn't as good. Clock rates are stalling, and in general, it's getting harder and harder to process this data with traditional systems. So as a result, we can no longer do the processing in many cases on a single machines, and it has to be scaled out to larger and larger clusters. And these are some pictures here from a Google data center. And with these large clusters, users are also adopting a new class of systems to actually do data processing. So for example, MapReduce, which is Google's programming model for its data centers that they wrote about in 2004, is now used at a number of companies that have nothing to do with the web or web search. So for example, companies like Bank of America and Visa are using Hadoop MapReduce, the open source implementation, for applications such as fraud detection. And this market alone, the Hadoop market, is projected to be a $1 billion market by 2016. So as a systems researcher, this change to a new class of these commodity clusters is both exciting and challenging. And so first, let me start with why it's exciting. It's exciting because this is a new kind of hardware environment that requires a new type of software stack. So normally, when you do computer systems, it's really hard to do things that have immediate sort of impact or effect in terms of how people operate in industry. But this is an area where people are adopting new algorithms, new systems, even new programming languages to deal with big data. And so there's this kind of unparalleled opportunity to actually affect what the software stack for these systems will be. At the same time, it's also challenging to work in. Apart from the challenges of just scale and distributed systems that come with the field, there are also growing demands in what people want out of their big data systems. In particular, there are growing demands about performance. Users want to be able to do analysis faster, or for example, instead of doing it in a batch mode, to do it in real time. There are growing demands about flexibility. So users, by that I mean just users want to run different types of applications at large scale with different computational requirements, and about availability, which I mean just high availability. So when you're Google and you're doing the web index every night, maybe it's okay if it doesn't make it one night. But when you're Bank of America and you're trying to do fraud detection, in real time, every minute that is down, you're actually losing a significant amount of money. So my work has been a software stack that tackles two of what we saw as the core problems in this field. And these are programming models and multi-tenancy. So for programming models, there's been a lot of work initially on batch processing models that work on large clusters. And that's been great. But users wanted to do much more than batch. And in particular, we looked at how to support interactive computations, complex algorithms that are not just one-pass aggregation over the data, and streaming computations in these large clusters. And in terms of multi-tenancy is kind of a core problem in operating systems and networks, but it's especially critical in these large systems because they're expensive. So within an organization, you'll have many groups that need to share this resource. And we came up with a number of algorithms to share these resources effectively in these large clusters. So this is kind of a picture of the systems and sort of algorithms I worked on. So at the top, we have Spark, and Spark Streaming, which are parallel execution engines that target different kinds of workloads. In the middle, we have Mesos and Orchestra, which are two resource-sharing systems that are about sharing the cluster among diverse data center applications. And then in the bottom, I've worked on a number of scheduling algorithms that I've applied both in these systems that we built and in existing systems like Hadoop MapReduce. And these are both about what's kind of the right policy to divide resources and about how do we improve efficiency. So there's stuff like how do we do fair sharing of multiple resources or data locality or dealing with stragglers. So the systems at the top address the first problem I talked about of programming models. The systems at the bottom are about multi-tenancy. So in this talk, I'm going to focus mainly on the area at the top. I'll talk about the more powerful programming models. And then at the end, I'll speak a little bit about one of the problems that we studied algorithmically as well. So let me just start with some really basic background on these kind of programming models for large clusters. So when you want to program a large commodity cluster, there are really two things that make it hard and that make it different from previous parallel programming environments, like a multi-core. And these are failures and stragglers. So failures essentially are amplified at scale. So if you have a server, a typical server today, the mean time between failures might be 3 years. So that's okay if you have a single server. But if you put 1,000 of those together, you get a mean time between failures of 1 day. So just because it's happening 1,000 times more often. And if you put 10,000 of them, you're going to see 10 failures a day. So this is something that these systems need to deal with. And the second problem is called stragglers, which is a node hasn't just crashed completely, but it's just going slowly for whatever reason. And this is actually much more common even than failures. Some reasons node might be going slowly are just contention between different applications or bugs in the operating system or actually hardware that's kind of failing but hasn't quite gotten there, like a dying disk. And I think everyone who's had a laptop with a disk has seen that problem. So MapReduce was the kind of a system that really inspired a lot of the work in this area. And it was published by Google in 2004. And the cool thing about MapReduce is that it handled these two problems automatically. So MapReduce itself, if you haven't seen it, it's this pretty simple, like one-pass aggregation pattern where you give it a map function to run over the data in parallel, and then a reduce function to aggregate the results of that. And you write the output into a replicated storage system. But the part that's cool about MapReduce is if one of the map tasks is slow or one of them goes away or whatever, it knows how to launch a second copy of that and splice it into this computation and still produce a result. So MapReduce was great in terms of simplifying batch processing, and it's been adopted very widely. But what we saw is that as soon as people started using it, they wanted to do much more than this kind of one-pass batch processing. And in particular, people wanted to do 3 things. So one of them was more complex algorithms, multi-pass algorithms that don't fit well into the one-pass MapReduce model. And one example of this is iterative algorithms, which are very common in machine learning or graph algorithms, where you go over the same data multiple times and you converge to some kind of fixed point. Second thing they wanted to do is interactive ad hoc queries. So you compute, say, an index of the web or statistics about it every night. That's great. But if I have a new question that you haven't pre-computed, how quickly can I interactively ask that and get an answer? And the final thing people wanted to do is real-time processing at large scales. So, for example, you develop a spam detection algorithm and you run a training every night to actually train a spam filter. But now, can you run that training in real time to deal with new types of spam campaigns as they arise? So one reaction to these needs is that people have built a wide variety of specialized programming models and systems for these new applications. So just as an example, Google published Pagel, which is a specialized model for graph computation. It's centered around passing messages along on a graph. There have been a bunch of implementations of iterative MapReduce that add support for looping a MapReduce computation. And the popular system in open source nowadays is Storm, is a system from Twitter for stream processing. But there are two problems with this approach. One problem is that the specialized cases that have been considered may not actually cover all applications. So if you have an application that is computationally very similar to, say, iterative MapReduce or to Pagel, but it's not easy to express with those models, you kind of have to start from scratch and build a new specialized system for it. And the second problem is that even if these cover all your bases, all the things you want to do, it's hard to compose these into a single application. And in reality, people want to compose different models. They might want to say, run a graph algorithm to produce a graph, and then run a machine learning algorithm on the result. And they don't want to have to write that in separate systems. So our approach here was to observe that these applications, complex, interactive, and streaming, which seem fairly different at first, actually all have one thing in common that they need and that MapReduce doesn't have, which is the reason why they're not efficient with MapReduce. And that thing is that they all require efficient data sharing between multiple parallel operations. So I'll show what I mean by that. So just as an example, if you have iterative algorithm, for example, something like PageRank, this is a very common pattern. Basically, the way it's going to work is you'll have a bunch of different steps. Each step can be written as a MapReduce, but in between them, you have to store data. And the output of each step becomes the input of the next one. So in PageRank, for example, the way you'd do it is you'd probably, you'd read your graph from an input, you'd do a MapReduce to compute the initial PageRank of each page, and now you'd have to write that out. And then you'd load that back in, use that to compute the next iteration of PageRank, and write the state back out. And in MapReduce, you have an abstraction for the computation, the blue box is here, but you don't have one for storage. So you're stuck with, in this case, a distributed file system, which turns out to be really slow for this kind of application. Similar things happen with interactive data mining. Often when you're doing interactive queries, you want to select a subset of the data that you care about and then ask a bunch of questions about it. And again, the storage abstraction for this thing here is the file system. And I'm gonna come back to streaming later on, but streaming turns out to involve a lot of data sharing as well, because streaming is all about maintaining state as new data arrives. So when people do this today, they use this kind of distributed file systems. And the distributed file system is actually quite slow for a couple of reasons. One is that it has to replicate all the data you write across nodes. And that happens at the speed of the network, which is actually quite slow compared to the speed at which you can compute stuff on a machine. And second, they actually write it to disk for reliability as well. And that can be even slower than the network. So these things make it slow, but I want to point out that they're also necessary for fault tolerance. That's why distributed file systems replicate this data. So in our work, we wanted to be able to do this sharing at the speed of memory, and to make it really, as fast to share data on a cluster as you would in a program running on a single machine. And the reason is very simple. The access rate for memory and for computation within a single machine is much faster than these other things. So for example, even the fastest data center network people might commonly deploy today would be, say, 10 gigabit Ethernet. Most people have 1 gigabit, but within a modern server, you can easily get like 400 gigabits of actual work done if you want. So that's why we want to do this in memory at the speed of memory. And then the challenge is, how are we going to make it fault tolerant? Now, there have been a bunch of storage systems for in-memory cluster storage system, but it turns out they don't actually meet this goal we have of efficiency. So most systems today are based on this general purpose shared memory model, where the abstraction is that you have a big distributed table and you can read and write in individual cells in the table. We call this fine-grained updates. And examples of this are parallel databases, key value stores, RAM cloud, distributed shared memory, which is a very popular thing in the past as well. And so the problem with this is that to do fault tolerance, you still have to replicate the data or maybe logs about what you did over the network, because all you see are these like reads and writes to cells. And that's slow. As I said before, it's 10 to 100 times slower than actually writing to memory. So the question we looked at is, can we provide fault tolerance for these applications without requiring replication? Yeah?
Yeah, can you just speak about the trends on those speeds?
The trends on these speeds. Yeah, good question. I think in general, all these access rates are growing, but I think there's still, I mean, memory is, as far as I know, is growing at least as fast as the network. And disk capacity, actually, disk access rates have not been growing. So that's actually really a big problem. Yeah. Yeah, so these, yeah, but I think these trends will continue. In general, it's harder to have a fast network that spans, like a whole room as opposed to, one machine. So yeah. Okay, so yeah, so that's what we wanted to do. Can we provide fault tolerance without relying on replication? So the solution we came up with is an abstraction called resilient distributed datasets, or RDDs, which provide a restricted form of shared memory. So instead of letting you just do arbitrary updates to this shared state where it's really hard to make that reliable, RDDs are restricted in two ways. First of all, they're immutable. Once you create one, you can't go and randomly change it. There's a lot of elements of like functional programming in here. And the second thing is that they can only be built through coarse-grained deterministic operations that usually you apply at the level of an entire data set. So for example, you pass a data set through a map function. And then what that helps with is that instead of replicating the data, we can do fault recovery using lineage, which is remembering the operations we did to build the data. So we just have to log one operation that you applied to an entire data set instead of having to log the result of that operation. And because we only remember the lost operations, the operations, there's very little cost. And if something fails, we can recompute it by rerunning that work. So just to show a picture of how this works, here's one set of operations we might do with RDDs. So maybe we start with an input file that's spread out across multiple disks in the cluster, and we do a map function. So map just means apply a function f to every element of this data set. So that's going to build the RDD. It will be in memory. This is how I'm going to depict it. So the oval is the whole RDD, and then the blue circles are partitions. And it's not going to be replicated. It's just going to be sitting in there. But we'll remember the function f. You might do another operation next, for example, group by. Group by has a more complicated dependency pattern, and you get out a new RDD. And finally, you might want to do something like a filter, and now you get back a final result. Now, if something fails, we can use this graph of dependencies to recompute it. So for example, if this guy here goes away, we can go and rerun the function h on the input partition and get that back. Even if multiple pieces of the data go away, we can recompute them in kind of the order that was required. And a thing it's a little subtle, but I'm going to show more later, is in practice, when a machine fails, you don't just lose one partition of the RDD. You design it so that you have many small partitions, and when a machine fails, maybe it had 100 partitions, and then you can recompute those in parallel across the cluster. So recovery itself can actually be quite fast. It's not just recomputing stuff from the start. So that's kind of the model. We're going to have these immutable coarse-grained operations. So our next question is, how general is this? Can we actually write useful applications with it? And what we found is, actually, despite the restrictions, RDDs are actually quite general, and they can express a lot of the parallel algorithms in use today. And the reason for that is that a lot of parallel algorithms are data parallel. You just express them in terms of applying one operation to all the elements of a data set. And so because of that reason, this strategy of remembering the operation instead of remembering the data makes a lot of sense. So in fact, we found that we could unify many of the programming models that have so far been proposed as separate systems. So these include the data flow models like MapReduce or generalizations of that like Dryad, which fit well into the kind of transformations I showed before. But they also include some of these iterative algorithms. So for example, Pregel, which looks like message passing on a graph, can be expressed efficiently using RDDs. So can iterative MapReduce and PowerGraph, which is a graph processing model from Carlos. And the final thing is that we were able to support new applications that some of these models don't. So I'll talk, for example, about stream processing. So just to put this in perspective, here's kind of a trade-off space that shows RDDs as a storage abstraction. And basically, this is comparing 2 dimensions, the granularity of updates you allow and the write throughput. And so on the left, we have things like key value stores, databases, RAM cloud, which are in-memory storage systems. They allow fine-grained updates, but they're limited by the network bandwidth in terms of throughput. Distributed file systems like the Google file system actually aren't really designed for fine-grained updates, but people have been using them successfully for batch processing anyway because of the parallel nature of the algorithms. But they're also limited by this network throughput. And finally, RDDs, as long as you're willing to stick with coarse-grained operations, they can be limited by just memory throughput. Okay, so that's kind of the Spark. That's kind of the RDD model. We implemented the model in a system called Spark, and I'll talk a little bit about that as well. So Spark lets you manipulate RDDs through this pretty concise functional programming interface in Scala. Scala is a language, it's basically functional programming on the Java VM. And actually, we support Python and other languages now, too. And one of the cool things we did is that you can use it interactively from the Scala shell. And basically, you pass it a function, and we're going to ship that function and all the variables it depends on to the cluster. So just as an example, this is some really basic Spark code. Basically, you create a data set that represents a file. HDFS is the Hadoop file system. And then you might apply filter. And this here is Scala's syntax for a function literal or a closure. So this is like lambda x, x that starts with error. And you can do a bunch of these transformations. So to show you that, I wanted to actually show you this thing live instead of just going through some code examples, if the internet still works. So basically what I've done here, I've set up a Spark cluster on Amazon EC2. It's got 20 nodes. And I loaded a copy of Wikipedia on it, which is a 60 gigabytes. So it's not huge, but it's not a thing you want to deal with on a single machine. And we're going to do some searches of Wikipedia, just like plain text search. So this here is the Spark shell. Let me move that up so people can see it a bit. And here you can do kind of your standard stuff you do in an interactive interpreter, but you also have this special variable, Spark context, or SC, which is used to do stuff in parallel on the cluster. And the first thing I'm going to do, I'm going to create a RDD that represents a file in the cluster. And this is in the Hadoop file system. So that's what this is going to be. And that's going to be file. And you can see this is an RDD that contains strings. It contains 1 per line. So we can actually peek at the data and see what the format is like. This is a tab-separated values dump of Wikipedia. And I'm just asking for the first line. It just reads that. And basically, each line in the file is a tab-separated record about 1 article. So this is the article ID. This is the title. This was maybe the alphabetically first thing in Wikipedia. This is the date when it was last modified. And there's an XML version of the content. And then you don't see it, but there's a plain text version of the article as well as a 5th field. OK. So now what we're going to do with this is some transformations. So I'm going to pull out from each article. I don't want to deal with this whole mess. I just want to pull out the plain text, which is the 5th field. So let's do that. And basically, I'm going to take the file. I'm going to map. I'm going to take each guy and split it by tabs. And then I'm going to also do a filter. So some of the articles don't have the plain text field. They're things like images. So I'm going to filter x.size equals 5 so that they have exactly 5 fields. And then I'm going to map, we have this array of fields now, and I'm going to map out field number 5. Okay, so this defines another RDD of strings to this sequence of transformations. And now, for example, if I do text at first, it will be, oh, wait a minute. Huh, it's a little weird. Oh, you know what I did? I did 5 instead of 4. Let's just do it that way. Yeah, sorry about that. So if I do, you can see it's live, of course. It's not just me narrating a carefully orchestrated video. But that's one of the nice, yeah, whatever. So let's, let's do this again. So if you do text at first, right, this is the text for and yet and yet. And yet was actually an album in some kind of other weirdly named thing. So that's what it is. So final thing I'm going to do, I'm going to mark these things to persist. Persist just means keep the results in memory. By default, we don't keep like every intermediate result in memory. You have to tell us which RDDs you want to keep in memory after computing. So now let's do a query on the whole data sets. On the whole data set. And I'm going to take, so which of these texts, these are article texts, which of them contains Berkeley, for example? And just count those. How many articles mention Berkeley? And you can start, taking your bets now. So what it's going to do now, it launches these 480 tasks in parallel on the cluster, and they're sitting there and running. And basically, it's shipped the code I typed into the cluster to actually run it over there. So it's going to go ahead and hopefully give us back a result. OK. So yeah, so basically the answer is 15,000. 15,000 articles contain Berkeley. But that took 22 seconds. It's not that nice. So let's try to do it again. And now that we did it once, the data will be in memory. So if we do this again now, you can see you get back to the same answer in about half a second. And having this really changes the size of data that you can work with interactively. So just to show that, we can ask other questions too. The one I like to do next is Stanford. So Berkeley was 15,000. Let's try this one too. And this one's only 13,000. So I hope no one's from Stanford. Washington. Good, very good question. Yeah. There you go. So Washington is way ahead. It's not even noticing these guys. Washington is pretty happy there. Okay, so that's kind of how you use the system to do this stuff. And there's one other thing I wanted to show, which is sort of the risky part of the demo. So the things are called resilient. And let's see what happens if we actually get rid of some nodes. So if you look at the UI here, we had 20 nodes. I'm going to just take one of them and get rid of it. So, OK, goodbye. There we go. And it takes a little bit of time to actually shut down. But if we look, eventually, it will drop off out of here. Yeah, let's just give it a few seconds to fall out. OK, and now we're at 19. And if you look here, this guy has also been notified that it's gone. So let's do Washington again. It was 120,000. And let's just do it again with this. And basically, you can see, so you can see at the end there, it lost about 30 partitions of the data. But the cool thing is the recovery only took about 4 seconds because we were able to do that recovery in parallel. So this is kind of the cool thing about doing it this way. You can actually recover from faults pretty quickly if you're in a large cluster. So that's that. And we can defer further comparisons of like Wikipedia accounts for later. It's like the first thing we started to do with the system is search for things in Wikipedia. OK, cool. So that's kind of the programming interface. We've used this to implement sort of more realistic algorithms as well, not just searching Wikipedia. So for example, in these iterative machine learning algorithms, we were able to see similar speedups of what I showed. And depending on the algorithm, it can go somewhere from 5 or 10 to 100 times faster, depending on how CPU bound the algorithm is. So here I'm showing k-means and logistic regression and comparing against Hadoop MapReduce. And the nice thing here is comparing against Hadoop MapReduce is a little unfair because it wasn't designed for these. But a bunch of other people have built in-memory processing engines, and we get similar speedups to them. But most of them didn't have this kind of fault tolerance that we did. At best, they had maybe some checkpointing periodically. So we're able to do this while still achieving the kind of fast fault recovery I showed before. Okay. And we've used this to implement other programming models on top as well, so to show the generality of it. So we've been able to implement both kind of the more standard MapReduce and Dryad and a bunch of these new things that people have proposed, often in very little lines of code. So we did Peggle, iterative MapReduce, and GraphLab were able to do the synchronous version. GraphLab also supports asynchronous, which is really useful in some cases, but it's less deterministic, so it doesn't fit into this model. But this is still useful for a bunch of stuff. One final thing we did here that's kind of cool is SQL. So in the database community, there's been kind of this debate between parallel database systems, which are very fast but don't usually provide fault recovery within a query, and MapReduce, which is often like 10 or 100 times slower but supports fault recovery in the middle. And in our system, Shark, which is actually going to appear at SIGMOD this year, we were able to get the same kind of speed-ups over MapReduce that the parallel databases did while retaining the fault recovery by using RDDs. And so, yeah, and the reason we were able to do all these is what I said at the beginning. They're all based on coarse-grained operations, so it makes sense to do this model. Final thing I want to add here is it's not just a matter of like, oh, our thing is more general. It's also having this ability allows users to intermix these models. So for example, in Shark, you can do your SQL query, and then you can run a k-means clustering on the result. And it's all in the same system. You don't have to write the data out and pay the cost of moving it across systems. So this is what's exciting to us. And Spark is, apart from being a research project, it's also an open source project. And we've been fortunate to have a growing community of people who are actually using it for applications. So just some numbers on that community. We held a training camp last summer where 3,000 people watched the stream online. We have a meetup in the San Francisco area with more than 500 members. And in the past year, 14 companies have actually contributed code to Spark. And it's really great to have these guys, even just from a purely research point of view, because you get to see a lot of new problems and much more exciting things than k-means and Wikipedia search that people are trying to do. Okay, so that was kind of the Spark part, covered most of the top half. But the one thing that I haven't gone into yet is streaming. So I'm gonna talk about that real quick as well. So the problem in streaming was now we've done batch, we've done interactive and complex analytics. How can we also do fault-tolerant streaming computation at scale? And the motivation for this is pretty simple. A lot of the big data applications today receive data in real time and have significant value to actually processing it in real time. So things like fraud detection or spam filtering, it's very clear that doing those faster is better. Even things like statistics about your website, you might want to understand what users are doing after you push changes to it. So it's important there. And companies like Twitter and Google have hundreds of nodes that run streaming computations to deal with these data streams. So just to set kind of expectations, our goal here by streaming, we really mean like half a second to 2 second latency. We don't mean the millisecond financial trading kind of stuff. And but we want to do it at a scale of hundreds of nodes. Unfortunately, streaming is also hard to do right. And that's because these issues of failures and stragglers become really serious problems at scale. So fault recovery, which I showed before, faults are kind of a nuisance when you're doing interactive stuff. But if you fall behind 10 seconds in your streaming application, you might be losing the whole point of actually doing that application. And same thing with stragglers. If a node is going slowly and the system has to wait for it to catch up, that's going to be a serious problem as well. So there's been a bunch of work on streaming in the past, but most systems use this, what I'm calling a continuous processing model that makes it difficult to deal with faults and stragglers. And just to summarize that, basically the model here is really natural. It's basically each node has a bunch of state that's in memory, and basically state is the thing that really makes streaming hard. So for example, you have an application that needs to count how many people clicked on each URL. And so state is a big hash table of like this URL and this count. Basically, these nodes pass records between them. And when a record arrives, you can update your state and push out new records to other nodes. So this is a really natural model. It really helps to minimize latency, but it turns out to be hard to deal with faults. And basically, there are two ways people have done fault tolerance, replication and upstream backup. So replication is the most common one in the database community, and it's been used in systems like Borealis and protocols like Flux. And the idea there is you're going to have two copies of the topology I showed before, and you're going to send input to both of them. Now, the thing that makes the application hard, though, is you also have to keep the copies in sync. So there's a lot of subtlety there in the algorithms to do that. Basically, the problem is that the state here might be determined on the order by which messages arrived from the nodes above. So, a record gets sent to node 1, one gets to node 2. Which one did you receive first? That might affect your state. So your copy here of node 3 needs to agree with this copy at the top on the order it saw things in. And this is a thing that, apart from leading to complexity, can also add overhead. So basically, replication, you can recover from faults quickly because there's another copy there, but there's a factor of at least 2 of hardware cost. And we thought this is really expensive to do at scale. Upstream backup, the idea there is a little different. You take checkpoints every so often, and then each node buffers data it's sent since the checkpoint. And when something fails, you just launch one backup copy of the node, and you recover that. And upstream backup has less of a hardware need. You only need kind of the one node to tolerate one failure, but it can be really slow to recover, especially at high loads, because the node has to not only recompute state that was lost, but also catch up with the arriving stream. And finally, a bigger problem in both systems is that neither of them deal particularly well with stragglers. So if you have a node that hasn't failed, but is just going kind of slowly, in the replication approach, because of synchronization, you have to keep the whole system in pace with that slow node. And so that's going to really mess things up, when you're running a large-scale system. And in the upstream backup, you don't really have anything you could do except treat the slow node as a failure. So for these reasons, we didn't want to do these approaches. So in our system, we wanted to design a system that can meet a set of fairly ambitious goals. So we wanted to be able to scale to hundreds of nodes and to have minimal cost for the computation beyond the base processing, so definitely not 2x replication. We wanted to tolerate both crashes and stragglers, and we wanted to be able to achieve sub-second latency and sub-second fault recovery. So how did we do this? So our observation here was to start with the batch processing models. And we noticed that batch processing models like MapReduce or Spark, which I showed, actually have a really efficient way of providing fault tolerance, which is deterministic replay. So basically, these divide the application into deterministic tasks. And then when a machine fails, or even if it's slow, you can launch another copy of the task on a different machine and rebuild its output. So our idea was, could we run streaming computation as a series of small deterministic batch jobs? And then if we can do that, if we can do the engineering to make these small enough, we will be able to use the same recovery schemes just at a smaller time scale. So like, recover in half a second from a failure. One of the challenges is we have to keep state between these, across time. But we already had an efficient data sharing abstraction for state, which was RDDs. So that's what we end up doing. We call the model discretized stream processing. And basically, the model is we divide time into these little intervals. And in each interval, we take the data that arrives, and we store it reliably across the cluster. And when that interval is over, it forms an immutable data set, which is partitioned across the cluster. This one we actually replicate for fault tolerance because most people want to save the input, and you need to have some copy replicated if you want to recover from faults. Now, when the time step is over, we run a deterministic batch computation, like imagine a little MapReduce, and we produce new data sets. And these are also, I guess it's kind of hard to see, these are also immutable, but they're not replicated. They're just stored as RDDs. They're stored in memory. And these can be either the output of the computation or state for the next time step. And then on the next time step, you can do another deterministic operation based on your state from before and your new data. And finally, to recover from faults, we do the same trick I kind of showed in the demo. So one of the things we have to do here is we do have to checkpoint the state periodically, but we do that asynchronously because it's not, you don't have to do it for correctness. It's more of a performance thing. So we periodically do checkpoint some of the state. And then if a node fails, we go at that dependency graph and we recompute the lost partitions in parallel. So for example, here's kind of what we saw in the demo. This node fails and we lose some partitions. We go ahead and recompute them on the ones below. And compared to other systems, this gives us faster recovery than upstream backup without the cost of actually replicating everything. So yeah, so that's kind of the model. We're going to do these small deterministic batch jobs and split them into even smaller tasks so that we can recover quickly on failure. So next question is like, how fast can we actually make it go? And we found here that we could actually make it go pretty fast, at least compared to other systems. And we also made it scale pretty well. So we were able to process over 60 million records per second, or 6 gigabytes per second of data on a 100-node cluster at sub-second latency. And these graphs here show the scaling for 2 applications. grep is just searching for a regular expression, and top k is actually a sliding window, and then a word count, and then a top k. So it's kind of like a 3-stage MapReduce job. And this is running up to 100 nodes. And the lines there show if you put a latency target of 1 second, so our latency there was maybe 700 milliseconds, or if you put it of 2 seconds, you can get slightly higher throughput. But even with a 1 second latency target, we are actually scaling pretty linearly and performing pretty well. Compared to existing systems, there's no reason to expect our stuff to be faster necessarily than existing systems, but we wanted to show that it's in the same ballpark. And compared to Storm, for example, the open source streaming system, we're actually going 2 to 5 times faster, mostly because they seem to be limited in the number of records per second per node that they can process. And commercial database systems, they report numbers like 500,000 records per second. But that's usually on just one node, and they don't really scale out to many nodes. So we were able to do that per node and to also scale linearly to 100 nodes. And the other cool thing here is the fault tolerance properties we provide. So Storm, for example, doesn't have full fault recovery, and the commercial systems tend to use application. One final thing I want to show on this is the actual speed of recovery. So when something fails with discretized streams, we can also recover quite quickly in the same trick that I showed before. So this here is a graph from sliding window word count on 20 nodes with a 10-second checkpoint interval. And basically, in the time step where a node fails, we take about an extra second to recompute that data. And then we have this kind of window. This 10-second window is because we're doing an incremental sliding window. So during these 10 seconds, we actually subtract out data from 10 seconds ago, and we may have to recompute that. So there are a few bumps in that as well. But overall, we're kind of back in business pretty quickly, even if something fails. And another neat thing is the way the fault recovery scales with checkpoint interval and cluster size. So in this graph here, I'm showing first, what if we increase the checkpoint to 30 seconds? So this blue line here is a 30-second checkpoint and the same 20-node cluster as before. And there, the recovery takes about 4 seconds. So it's still not too bad, given you are doing 30 seconds of work. And then what if we increase the number of nodes from 20 to 40? And when we do that, the recovery time actually drops, which is great because we have more nodes to work in parallel to recover lost data. So I think that's one of the really cool things about this model is that parallelism is an asset and recovery gets faster with more nodes. Whereas in many previous systems, the bigger scale it was, the more things could go wrong and kind of the tougher it was to get it all to work. Okay. So that was kind of the bulk of the talk to programming models. So in the last bit, I also want to show you one problem we did on scheduling algorithms because I think it's kind of fun, and then I'll answer questions and things that people have. So as I said at the beginning, a major problem in these systems is kind of the traditional OS problem of resource sharing, and these systems are very expensive to build, and lots of groups want to use them. Imagine in a company like Google, how many different products want to do data analytics. So it's important to share them effectively. So one of the problems we looked at there that I'll talk about is multi-resource fairness. So that's just to set this up. Computer systems have been doing resource allocation for a long time. And one of the main ways they've been doing it is called fair sharing or weighted fair sharing, or in the operating system literature, it's sometimes called proportional sharing. Some examples of this are fair queuing on your network link or lottery scheduling on your CPU. And fair sharing basically takes one resource and divides it between users according to weights. So for example, if all the users have equal weight, they each get 1/3 of the resource. Now, the problem we faced is that in cluster applications in particular, different applications have different demands for different types of resources, and there isn't really like one resource you can divide fairly to keep, to actually do a decent allocation. So for example, some applications are CPU bound, some of them are memory bound. I just talked about why you want to do that. Some of them are networking or IO bound. So our question was, how can we generalize fair sharing to multiple resources? Just to give an example, we might have a cluster with, say, 100 CPUs and 100 gigabytes of memory. And I'm going to have two users. The first user wants to run a bunch of parallel tasks, and they each use 6 CPUs and 1 gigabyte of RAM. The second user wants to run tasks that use 3 CPUs and 4 gigabytes of RAM. So they just have different demands. So how many resources should you give to each user? So we tried a number of policies, and then we found some problems with them that don't arise in the single resource case that led to like our actual solution. So let me just show you actually two of the things we tried. So first thing we tried is what we called asset fairness. It's a pretty natural thing. The idea there is let's equalize users' overall fractions of the resources. So kind of imagine having 1% of the CPU is worth, say $1. Having 1% of RAM is worth $1, and we want to equalize everyone's dollar value. If we do this in the demands I had before, the 6.1 and 3.4, this is the allocation we get. So basically, first user gets 6/9 of the CPU, 1/9 of memory. The second gets 3/9 of the CPU and 4/9 of RAM. And they each have gotten 7/9 in total. So it seems pretty fair. Now, unfortunately, there's a problem with this allocation. So if you look at user number 2, that user has gotten less than half of both the CPU and the memory. And that seems kind of unfair. If their weight is a half, they're paying for half the cluster, why are they getting less than half the total resources? So we say this violates a property we call sharing incentive, which is that user, in a n user cluster, a user should be at least as well off as if they ran in like a private cluster of 1/n the size. And this isn't true here. Another approach we tried is called bottleneck fairness, in the one you see above, maybe you say the problem is we counted this user 2's memory against them, even though the first user wasn't using memory. I mean, it's not a bottleneck. Why are we penalizing people for it? So bottleneck fairness, the idea there was to equalize the share of the bottleneck resource, whatever gets filled up first. In this case, this was CPU. And if you do these allocations, this is what you end up with, half the CPU to each one, and you split the RAM however it works out. One problem with this one is that users can actually cheat the system by lying about their demands. So in this case, for example, user 2 can say, well, I don't actually need memory for my tasks. I only needed 1 gigabyte of memory. But if I tell the system I need 5, the bottleneck is going to shift to memory, and then I'll actually also get more of the CPU. And so it's kind of this bad incentive to actually lie about your demands in order to get more resources. So we say this is not strategy proof. And so both these things are situations that couldn't happen with a single resource, but do happen if you're not careful with multiple ones. And so our approach here was to determine a bunch of these properties and then come up with a policy that satisfies them. And to cut a long story short, we came up with something called dominant resource fairness. And the idea there is to equalize each user's share of the resource that user has the highest demand for. So here for the first one, it's CPU. For the second one, it's RAM. And they both get 4/7 of it. And we were able to prove that you'll always get, like in this case, at least half of that resource. And also, there's no benefit to lying about your demands here. And this is a thing we're actually starting to apply beyond data centers to things like middle boxes and software routers as well. So final thing I want to talk about is open source systems. So I really like building sort of realistic systems. And one of the things I've been fortunate with, I've open sourced a bunch of stuff, and I've been lucky that people have actually tried to use these in real applications. So I talked about Spark and Shark, but some of our other systems have some users as well. So the Mesos cluster manager we built to share resources has been adopted by Twitter. Actually, there's a Wired article today about it from Twitter, and they're using it to manage over 3,000 nodes to do resource sharing in their clusters. DRF, which I showed, is now implemented, is being implemented independently by the Hadoop developers in Hadoop 2.0, so that's great. An algorithm I worked on called Late for dealing with stragglers is included in Hadoop MapReduce as well. And so is delay scheduling, which is an algorithm for data locality. And actually, the scheduler I built for that, the Hadoop Fair scheduler, is one of the most widely used job schedulers for Hadoop today. It's been running at Facebook, for the past 4 or so years. And final thing that's been a lot of fun, but I don't have time to talk about, I did this project on a new algorithm for sequence alignment called SNAP. And this is actually it's basically like a 10 to 100 times faster algorithm to do this problem. And this is being used at UCSF in a virus discovery pipeline. This is one of the things I think is very exciting about this big data space, is that people really need these algorithms today, and you can actually build stuff that they use. So to summarize, I hope I've convinced you that big data systems are interesting to look at. They're kind of here to stay in the industry, at least for a while, and they present a bunch of new research problems. I talked about 2 of the problems. I talked about fault-tolerant, low-latency processing, where we proposed this idea, RDDs, that uses the coarse-grained nature of the operations. And I talked about multi-tenancy, where we proposed a bunch of algorithms, such as DRF. And that's it. I'd be happy to answer any questions.
We have time for a few questions.
So one of the fundamental things about Spark is that it only works on things that fit in memory. And you mentioned at the beginning that disk is the cheapest resource. And sort of scaling big is
good question. Does it only work on things that fit in memory? So that's actually not true. You can have RDDs that are backed by disk or by SSDs or whatever. And in fact, our implementation is designed to do sequential I/O. So when you fall out to disk, it actually performs similarly, in some cases better than Hadoop. So for example, in our work on Shark, we showed that even with on-disk data, we can go about 10 times faster than Hadoop by doing smarter things for SQL. So we've taken, my view of this is when you design your algorithm, you shouldn't worry about the size of the cluster it runs on. So whether you run it on like your one machine, your laptop, and it's going to take a day, or you run it on a cluster and it's going to take a minute, should be the same algorithm. And it will use whatever resources are available. Yeah.
So some stream processing algorithms are doing estimation and are not deterministic. They use probabilistic methods. How would your system work if things were probabilistic?
Good question. So if you did probabilistic methods for stream processing, like sketches or things like that. So basically, as long as you use a random number generator where you seed it with a known seed for each task, the result can still be deterministic. So it's probabilistic from the point of view of the algorithm. You view it as a randomized algorithm, but you just run, it's a pseudo-random number generator. So if you fail, you run it again with the same seed. And people have done that to do things like Monte Carlo and sampling on top of Spark.
So we've had sort of 4 or 5 years or more of performance results that are 100 times faster than Hadoop across the board. So how do we get out of this regime of shooting down Hadoop and start to
shooting down Hadoop? Well, I think okay. To answer that question, how can we get down from shooting down Hadoop? You can convince people to use Spark, and then you'll have to shoot that down.
yeah. If I was to give a talk to him, he would say, well, convince people to use GraphLab, and if I were to talk to him, we give source.
No, it's a good point. I mean, the other thing we can do is compare across them. So I tried to do a bit of that with the streaming systems and even with the iterative algorithms, and to say like what we bring that's different from those. It's tough because a lot of people do use Hadoop, and it's compelling to show it. But I think we'll move away from that. I mean, for things I'm doing, I want to compare against my previous implementation on Spark, and we've done a few things where we've done that. Yeah.
Great. Any more questions? Cool. Let's thank the speaker then.
Okay.